Okay, so today I want to talk about morphological image processing. Uh, so morphological image processing is more like set theoretic image processing. Okay, the operations are set theoretic, and in this the objects in an image are considered as the subsets in the image, and additionally, just like we had in convolution, there is something called a structuring element. Okay, so we had a kernel for convolution. In morphology, it is called a structuring element, but sometimes it can also be called a mask or a kernel. Okay? So, but the function of the kernel in morphology is different from convolution. Okay, so in convolution, the kernel, so that operation of convolution is a linear operation. Okay, the kernel acts linearly, but morphology, it's just a set theoretic operation. Okay, so I'll describe a few morphological operations, the basic ones, and there are many combinations of the basic ones that can be made in order to come up with, you know, uh, the aim of morphological image processing is to identify or isolate interesting characteristics of the image. Okay, in the end, just like uh, the aim of any image processing kernels that we have seen so far. Okay, so you want to isolate something, you want to detect certain characteristics of the image, and for that this is one of the processes that can be included in the image processing pipeline. Okay, so uh, so we deal with two sets, objects in the image and the structuring element, which will be abbreviated most often as SE. Okay, so typically it is done on binary images, although the morphological processes can also be done on higher dimensional images. Sorry, or higher dimensional subsets or sets in which you consider other characteristics like color, okay, uh, or even more than one color space. But we will only focus on binary images where it is easy to see what the operations are doing. Okay. So the objects are considered as subsets of z cross z because our pixels are numbered by integers. Okay, so the objects are considered as subsets of z cross z, and they will look like this. Okay, so originally this is the object. Okay, so when you think of this as a set, you are thinking of these objects as points in this object. Okay, so all the points in this, so that's the set. Okay, so in an image, so you will have the entire image. So there will be the objects which will be thought of as foreground pixels, okay, or foreground of the image, and the rest of it will be thought of as the background. Okay, and when you look at the digital image, actually this object and this object will be represented in this way. Okay, so notice that if you have straight lines like this, which all of whose points go through integer, like uh, so if the x coordinate or the y coordinate is fixed for a certain line, then you will get lines like this. Okay, so all pixels in a straight line, or otherwise if you have any other line, then the pixels are going to appear this way. Okay, so this is, although it doesn't look exactly like this is how a triangle will look like in a digital image. And then for us, the set is the set that consists of objects is the set of these pixels in the foreground. Okay, so these are our foreground pixels in gray, and everything that's in white here is the background pixels. Okay, so we have two sets in this image. There is the set of foreground pixels and there is the set of background pixels. Okay, so that is how we consider any image. And the structuring element, so this is an example of a structuring element. So this is a cross shaped structuring element. If you think of it as an image, it will look like this. So there will be again foreground and background, and as a digital image, This cross can be represented by this pixelation. Okay. Of course, you can make this bigger. Okay. In which case you will have a larger structuring element here. Okay. So this is how you can think of foreground, background, and the structuring elements as sets. Just like in the image, the structuring element also has foreground and background pixels. Okay. There will be times when we care about the values at the background pixels and times when we don't care. Okay. So you will see in examples later that suppose this is filled with some numbers and there's a cross. Okay. The cross means we really don't care about what element comes there. Okay. Doesn't matter to our processing. So that is what the notation means. Okay. So here is an example of structuring elements. So what I would like to or stress here is reflections. What is meant by reflections about the origin? Okay, so this is one of the morphological operations that we will see from time to time, and in which the reflection of the structuring element will be required. Okay, so every structuring element will have a center. Okay, so center is the obvious thing that you can think of when you imagine it. Okay, so the center is just if this is a square element, then this pixel is the center. If this is a circular element, then the center might change accordingly depending on the shape of the element. The point which is sort of equidistant from the borders, that is the center. Now in this case, if you have a structuring element that's a square like this, then obviously this point or this pixel is the center. Then the rotation, the reflection across origin really means that in terms of coordinates, you're sending x comma y, any x comma y to minus x comma minus y. That is what reflection means in for structuring elements. Okay, so the reflection of this structuring element is this one. Okay, so this pixel moves to this. The reflection of this structuring element will look just like the original one. In this case, this is called a symmetric structuring element. Okay, so here, so this is B and the reflection is denoted by B hat. Okay, so this is B hat. In this case, or for this example, B is equal to B hat. In that case, we will say that this structuring element is symmetric. Okay, but of course, all structuring elements need not be symmetric. For example, this B and this B hat. So in this structuring element, this one is a background pixel and these are foregrounds. So if you take the reflection, then the background pixel comes up here. Okay, so these are not symmetric. Similarly, these are non-symmetric, these are non-symmetric. Okay. Here is an example of don't care elements, where what it means is we don't care what elements are put here. You may put any pixel value here. Okay, and when you reflect this, it looks like this. Okay, so these are still non-symmetric. Here is a larger example of B and B hat. Okay, so these are structuring elements, and how they work we will see in a moment. So there are many morphological operations, and we will look at only these. Out of these, translation, reflection, erosion, and dilation. These are the very basic ones. Okay, opening and closing can be expressed in terms of erosion and dilation, and the later ones. So once we do opening and closing, there's one more called hit and miss transform. Okay, so maybe I'll add it here. There is something called the hit or miss transform. So 1, 2, 3, and 5 together make up the basic morphological transformations. And this 4 and many more of these are operations that you can obtain from a combination of the earlier ones. Okay. So here I have put in a table from the text, which contains a list of a lot of binary morphological operations. Binary means you have a set, you have an image and you have a structure. So, so of these, well, translation and reflection are very easy to look at. We will look at these two and we will use them everywhere. Complement and difference are also easy to treat. Then erosion, dilation, opening, closing, hit or miss transform. These are some very basic transforms. Okay, so these 5 we will look at in some detail. And after that, these things, boundary extraction, hole filling, corrected components, convex hull, all these things. So uh, I will briefly describe these, but we will not go into details. Okay, thinning and thickening, I will talk a little bit about. Similarly, skeletonization, a little bit of description. But again, there are many things that you can do with morphological operations. Okay, so this table sort of contains the name of the operation, the equation, and some comments related to it. Okay, so these later ones I'm not going to look at in detail. You can look it up if you ever need to, use that in your processing. I will only describe the basic ones. Okay, so now let's begin with. So actually, let's begin with translation. Okay, translation is easy. So this is the notation used to denote translation. So B is a structuring element, and parenthesis B with the Z outside is going to be the set of all pixel positions C, such that C is equal to B plus Z for V in B. Essentially, what this is saying is that this structuring element B is translated so that its center lies at the position of Z. Okay, so that translation is denoted by BZ. Okay, so if you want to look at an image example, so here is your A. Okay, so suppose this is your image, and suppose this is the structuring element B. Okay, so this is the center, right? And suppose this is the pixel Z. Now, if you move this structuring element B to this position, okay, maybe I use another color. So if you bring it to this position, okay, then the center of B is lying on Z now. Okay, so this position of B is what BZ means. This is the translation of B so that center lies on Z. Okay, now if you if you had some other W, okay, so suppose this is pixel W, okay, and then when you put B here so that the center lies on W, this position or this set of elements that you've got here, okay, let me do green. So this set of elements is described by, this is BW in this notation, right? This set of elements here, okay, what you have here is your BC. Okay, so this is what the translation of B means. You take the structuring element, put it at the point Z, put its center at the point Z, then the set of elements that you get in this way covered by the structuring element, that is BC. Okay. Then let's look at the reflection. Reflection is what we saw earlier in those images. Okay, and so B hat denotes the reflection of B, and this is simply, if you take the pixel W, this is simply the set of all pixels that are equal to minus B for any V in B. Okay, in terms of coordinates, it means that you send xy to minus x minus y. Okay, so this is called reflection of B about its origin. Okay, I can understand that this might not explain it completely. Okay, there could be some ambiguities with this, so that is why I have written down what it means actually in terms of 2D coordinates. Okay, so B hat will denote the reflection of B. The complement, well, if you have an object A, then the complement is simply all those. So for example, here, this is your A, then the complement of A is just like in set theory, everything that is not in A, that is complement of A. Okay, so that is so the complement of A is denoted by A raised to C. The difference, okay, so the difference A minus B is defined as the set of points in A but not in B. Okay, so set theoretically, you're not actually just subtracting images. That's not how we are looking at it, because these are not the image and the structuring element are not the same shape or size. Okay. So the way we think of it is A intersection B complement, the set of points that are in A but not in B. After B has been placed over A somewhere. Okay, that is what we mean by this. Erosion. So this is what we'll start looking at now. Okay, so we'll assume that we understand what these four things mean, and we'll move on with erosion. So what erosion does is it sort of removes pixels on the boundary of an object. Okay, so how is that done? So this is the definition set theoretically. So this is the notation for erosion. A eroded by B is the set of all those pixels such that when you translate B by Z, then the entire set lies inside A. Okay, so it is the set of all pixels. So these pixels originally are in Z, are in A. So the set of all pixels in A such that the translation of B by Z is contained inside A. Okay, so that is the definition of erosion. What it means, so from this image it will be very clear. This is the image. Okay, this is the image. This is the object whose pixels are denoted by set A. Okay, and this is the structuring element. Okay, now although this is not pixelated here, we can very well think of it as being pixelated. Okay, so what we can do is we can think of, yeah, let's think of B as being something like this, and this is the center of B. Okay, then now if you place this center over this pixel, then you can see that is going to be B translated by this Z, and that B is going to lie here. Okay, so the B is going to lie outside of this. If this is your Z and you place the center of B there, then it goes out. Okay, so now BZ for this Z is not contained in A. Okay, then this pixel we will remove. You want to keep only those pixels such that this translation is completely contained in it. That is what we are calling the erosion. Okay, so if you want to compute this erosion, you will not keep pixels for which the translation lies outside it. So for example, this pixel will have to go. But on the other hand, if you have this is your Z, okay, and if you translate B by this Z, then it lies completely inside it. So this pixel will stay in the erosion. That's the idea. Okay. So now with this kind of element, if you do this over every element of it, okay, so this set is going to contain all those pixels for which this translation is contained in. So that means you will have to process this over all pixels of A. Okay, so this processing is done over all the pixels of A, and those pixels where this condition is not satisfied are the color is changed to the background. Okay, so for this, if the condition is not satisfied, we change the color of this from foreground color to background color. In this case, from blue to white. Okay, so this pixel will become white. Similarly, this will become white. All the pixels on the border are going to become white. Okay, and then, but inside, from here onwards, everything is surviving. Okay, so that's what this is. So all these pixels survive, but all these are deleted from A. Okay, and this is what is the set A eroded by B. Okay, so this is the meaning of erosion of A by the structuring element B. Now you can imagine that if your B was just 1 pixel, then there is no erosion, right? If B had only 1 pixel, like I was saying before, then it would fit in every of these, each of these. Okay, so taking B to be a 1 by 1 pixel gives you no erosion. And if you make B larger, you will erode more and more. So here is another example. So now the structuring element is not a square, okay, but it's a rectangle. Okay, so they have in the text here they have said that this length and breadth are D, and accordingly they have defined the dimensions of this V. Okay, so this I'm not taking into consideration right now too much. But the point is you have some rectangular element here. And then you want to look at the what the erosion looks like. Okay. So now if in this case what they have done is they have taken the same height as the image. And this is the center. So you can imagine that if this pixel is placed at all these positions, this part is going to jut out. Okay. Similarly, if the center is placed over these pixels, then the lower part is going to be outside. Okay. If it is placed here, it will still not fit. Okay. The only pixels for which this, when placed at those pixels, the whole structuring element lies within the image is this center. Okay, this center row of pixels. Okay, so that is exactly what will survive. Everything else will be eroded by this image, by this structuring element. Okay, so I hope the basic idea of erosion is clear. It is clear that the eroded set, how it looks like or what remains, depends on the shape and size of the structuring element. If you change the structuring element, then the eroded set changes. Okay, there are various possibilities for structuring elements, by the way. So you can have squares, you can have rectangles, you can have circles, but circles you will not have exact circles, right? So you will have approximation to a circle. Okay? Just like, because these are all integer coordinates, just like here you have a, yeah, so this could be an approximation to an ellipse. Okay, because this sort of encompasses, this is encompassed in an ellipse. Okay, similarly you will have an approximation for a circle, just like this is an approximation to a triangle. Okay, but yeah, so essentially with this kind of approximation, you can have structuring elements to be of any size and shape. So in this example, we are only looking at square and rectangle. Okay. So as I described, the effect of erosion is to remove the pixels along the boundary of it. Okay, how many are removed and and which ones are removed? Okay, that completely depends on the size and shape of the structuring element. And one important use of this is to sort of, if you want to shave off the boundary slightly, okay, then you can use a small b. So I shouldn't say 1 by 1. So maybe a 2 by 2 square or something. Okay. So for example, 2 by 2 or 3 by 3 squares. If you take 2 by 2, actually there will be a problem that so then what is the center? If you take a 2 by 2 structuring element, then there is a problem of finding the center. Okay, so it won't be at, so not 2 by 2. So the way out of that actually in most coding algorithms is that if you have even by even, then one of the corners is denoted as the center, just like for convolution we saw. Okay, so let me say, for example, 3 by 3 square. Okay, so odd by odd usually is taken because it is easy to keep track of. That's all. Also for reducing large blobs to small ones. Okay, so if you have, I will show you some image examples where you have some large components in an image, and now you don't need, or maybe you want to separate them out. Okay, then for such a thing, the boundary is eroded, and hopefully the objects get separated out. Okay, and then they are reduced to small ones which you can count. Okay, so for in such cases also erosion is useful. A geometric way of defining erosion is to look at all those pixels such that the intersection of the translation of B with the A complement is empty. Okay, so this is just another way of defining erosion. The translation of B by Z does not intersect with the background pixel. Just another way of saying that this is totally contained inside it. Okay. You might see one or the other. So if so that's erosion, and dilation is the opposite of erosion. Not opposite, actually, it's called morphological dual. Okay, I'll explain what it means. So, but dilation does the opposite of what erosion does. Erosion was removing some number of pixels from A. Dilation is going to add pixels to A. Okay. So the dilation of A by B is defined to be all those pixels of A such that when you translate the reflection of B through Z, then that intersects A non-trivial. Okay, so translation not of B, but translation of B hat by Z intersects A non-trivially. So this is a slight uh, twist in the definition of dilation. But if your structuring element is symmetric, then it doesn't matter. This B hat doesn't matter. B is equal to B hat. So that's easier to understand in the beginning. Just take symmetric structuring elements. So essentially, we are saying that you take all those pixels such that the translation of B along those pixels intersects A non-trivially. So in this, although yeah, one thing I should say here is that now this Z is not necessarily in A. Okay, so this Z is just so I haven't given the whole image any set name. So let I denote the set of all pixels in the image. Okay, so then this is the Z, all Z in R. Okay, so the processing will be done for all pixels in the image. And among those pixels, if you find a pixel such that when you place B hat on that pixel, the center of B hat on that pixel, the intersection of A, intersection with A is non-trivial, then you keep that Z as foreground. Okay, if it was background pixel, it becomes the foreground now. Okay, so you add it to the foreground pixel, and that is the dilation of A by B. Okay. So here I have just remarked is that if B is equal to B hat, which means B is symmetric, then you don't require this. Okay. So again, here there are some structuring elements and their reflections. And here, this is the effect of dilation. So we have the same object as before and a structuring element like before. Okay. Now this structuring element will be sort of placed at every pixel in the image. Okay. So if this structuring element like before, if it was 3 by 3 and we had that grid here, now placing it here, for example, suppose you have 3 by 3 structuring element and suppose it is placed at this pixel. Okay. Then there is no intersection with A. So this pixel stays as it is. It stays in the background. Okay. Similarly, for this pixel, there is no intersection, and so on. Okay. However, if you come close to the boundary, okay, and you look at maybe this pixel here, okay, then this 3 by 3 structuring element is intersecting a non-trivial, which means this pixel you will change from background to foreground. So you will suppose this is so white is the background 255 and some color, suppose this is gray. Okay. Then you will change that pixel color from background to foreground, from 255 to whatever gray scale value. Okay, and if you, so this processing being done over all the pixels of the image, then the original A has now sort of got dilated to this outer, the boundary has dilated to this. Okay, so the dotted line is the earlier boundary and this solid line is the new boundary after dilation. Okay, so this is how, so this structuring element now is changed from a square to a rectangle. Then this is the original boundary. After applying this dilation with this structuring element to the entire image, turns out that for all these pixel positions, the structuring element intersects A. Okay, so then they are all added to the foreground, and the dilated object looks like this. Okay, so you can imagine what is happening. This is doing exactly the opposite of what erosion was doing. Okay, now what we want to, the reason why this B hat instead of B, they have taken B hat, because we want to say this duality. So in morphology, duality means two operations which are uh, sort of the opposite of each other with respect to complementation and reflection. Okay, so these are called dual operations. So erosion and dilation are duals of each other with respect to complementation and reflection, which means that if you take if you erode A by B and take the complement of that, then that is the same as first you take a complement and dilate by the reflection of B. Okay, so and similarly the other way. So you can replace erosion by dilation here and dilation by erosion here. Okay, so these relations hold. These are duality relations between erosion and dilation. Essentially, the first property is saying that if you erode the foreground by B, then it is the same as dilating the background by B hat. See, A is the foreground, A complement is the background. So this is erosion of A, or erosion of the foreground by B is same as dilation of the background by B hat. That's what one is saying. Okay, and two is saying that if you dilate the foreground by B, the what you will get is exactly what you get by eroding the background by B. Okay, so these are duals of each other. So it is important that when this processing is being done, you differentiate between foreground and background. Okay, and it should be clear to you, you're operating on what. Are you operating on the foreground pixels, or you're operating on the background pixels? Otherwise, you end up doing the opposite of what you started doing. Okay. Yeah, and in the case when B is symmetric, when B is equal to B hat, duality tells us that eroding the foreground by B is same as dilating the background by. Okay, so erosion and dilation in this sense are opposites of each other. Okay, we don't say opposite, we say dual. If you erode the foreground by B, that is the same as dilating the background by B. Converse, and the other way also. If you erode the background by B, that is same as dilating the foreground by B for a symmetric structuring element B. Okay. So I hope erosion and dilation are sort of clear. Okay. So erosion is going to remove pixels on the boundary. Dilation is going to add in subpixels on the boundary. What is added, that depends on the structuring element. Okay. Then a combination of erosion and dilation gives us two operations called opening and closing, which we will see are also duals of each other. Okay, so the opening of A by B is defined in this way. So first what you do is you erode A by B and then you dilate the result by B. Okay, so first you do erosion, then on that result you do dilation with the same structuring element. This is called opening of A by B. Okay, the effect of opening, the result of doing all this, first erosion, then dilation with the same structuring element, it will smooth the contours, eliminate some narrow isthmuses, that is like narrow bridges, and remove some thin, sort of hair-like protrusions if there are there in the binary image. Those are removed. Okay, so actually let's just look at this example. So here is the foreground and this is the background. Okay, and the structuring element in this case is circular. Okay, so then essentially what happens when first erosion and then dilation is applied is that you get the union of, so this, I mean, one can show this set theoretically. Okay, I'm not showing it, I'm just writing down the definition. So geometrically that earlier definition can be reduced to this. It is the union of all translations of B which are contained in it. Okay, So this structuring element, suppose I put it here, then this is contained in A. So I'll keep this pixel in foreground and so on. You do this for each of these. Okay. So now, for example, this structuring element, when it comes here, okay, then some pixels are going to be left out. These corners will be left out, right? Similarly here. So the effect essentially looks like this. Okay. So yeah, this is the structuring element translated at various pixels in the foreground. These are some pixels that are left out. Okay, here. So here you can think of it as this gap was so narrow that the structuring element couldn't fit here. That is why it gets removed. Okay. So this is true in general. What opening will do is it will remove, or whenever there are these kind of, this is called an isthmus, which means a narrow bridge between two components. So this narrow bridges will be removed when the structuring element is bigger than that bridge. Okay. So the result of opening on this image or this object will be this. Okay. So you've sort of opened this bridge. Okay. Not only that, you have also smoothed the corners. These corners all become smooth. Also, one thing to note is that this is becoming smooth here because you are looking at a round or a circular structuring element. If you were looking at a rectangular or a square structuring element, you wouldn't necessarily get this. Okay, there will something will happen here. Okay, but this corner can stay as it is. Okay, so this is the effect of opening, right? And the closing is exactly the opposite operation. You first dilate A by B and then erode by B. Okay, and geometrically, just like we have this picture here, geometrically it looks like this. So this was the same foreground as before. Okay, and now you are going to look at first dilate, then erode. Okay, so for dilation, you have to process on all elements of the image, right? So you will look at all pixels in the image. You will do dilation and then erosion by B. Okay, so the net effect turns out to be the union of, or actually the complement of the union of all translations that intersect A trivially. So you look at all translations of B that intersect A trivially. Okay, take the union of all those. So these are going to be all translations that intersect A trivially, right? In fact, all these also. Anything outside this is going to be all those translations that do not intersect it. So we take the union of all of these, even outside, which they haven't shown. Okay, all of these, and then the complement of that. So that's going to be this. Okay, again, because this was a circular structuring element, what has happened is, since you're taking the complement of everything that's outside here, this little white region is included. Okay, so this caused a smoothing of the contour here. Okay, but here, these corners, there is no smoothing because, I mean, there was no, in this particular object and structuring element, there is no smoothing occurring here. Okay. So this is what closing does, and closing and opening, like before, are duals, morphological duals of each other. Yeah, what closing does is it fills these narrow gaps. So here actually there is no gap, but you can very well imagine that if this image was actually this one, okay, then you would have, again, because the structuring element is not passing through this, okay, it would have light outside here, and then this gap would have been filled. Okay, so closing, just as the name seems to say, closes narrow gaps. Okay, the gap has to be smaller than the structuring element. So it joins these narrow gaps or fills up the narrow breaks that are there between. If there is maybe a crack, okay, in the foreground there is some crack, then that crack will be filled up after the closing operation. Okay. Yeah, just this is what I was mentioning. Opening and closing are duals with respect to complementation and reflection. Okay. Uh, so the opening of the foreground by B, opening is denoted by this hollow circle, and closing is a dot. Okay. So the opening of A by B, that means opening of foreground by B, is same as the closing of the background by B hat. And if B is symmetric, this will mean opening of foreground by B is same as closing of background by B. Okay, so in that sense, they will be opposite operations of each other. And the other way also, that is the closing of the foreground by B is same as opening of the background by B hat. Okay, so these are duals. You can do one by working on the other. Okay, so I mean, why would you choose to work on background rather than foreground? Or why would the only I mean, one of the things that you might think of is how many pixels do you have to process? Okay, so suppose there are too many background pixels to process, you might prefer to do the processing on the foreground pixels. Okay, so that's the only consideration. Okay. Okay. So these are some properties that opening and closing satisfy. So morphological opening, the opening of A lies inside A. Okay, as we have seen here, this is the opening. As a set, this opening, that is these two together, lie inside of A. So opening of A is a subset of A. Then opening preserves containment. If you had a subset of A and you opened both A and the subset, then that earlier subset will still be a subset of the opened A. Okay. So opening preserves the containment relation. Okay. And if you apply opening again and again, it makes no difference. Applying it once is, or applying it more than once is same as applying it once. So the opening of A opened by B, okay, is same as A opened by B. If you apply again, the result is not going to change. The same is true for closing. Okay, so if you have applied closing once, then you don't need to apply it again because the result is not going to change. Okay. Now this property is saying that the closing of A contains A. This is the opposite of opening. Okay, so the closing of A is a larger set. Closing is going to make the set larger, and it's going to contain the original. Closing also preserves containment, just like opening. Okay, so these are morphological properties of opening and closing. So these are the basic ones: erosion, dilation, opening, closing. And one more that I want to look at is this hit or miss transform. So this is slightly different from the earlier four that we looked at, in the sense that so I have chosen to make a slightly simplified description of hit or miss transform, but the textbook does a more detailed job of it, describing it as uh, an operation that is done using two structuring elements. Okay, so what I am doing is I am sort of simplifying that. Instead of looking at two structuring elements, you can think of it as a structuring element. So till now, in all the operations, it was only the foreground pixels that mattered to us. Okay, when we say that B is contained in A, or the translation of B is contained in A, we only care about the foreground pixels being contained. We are not caring about the background pixels. Okay. However, in hit or miss transform, the foreground pixels as well as the background pixels will matter to us. Okay, so we will, when the processing is done, we have to check what happens to the foreground pixels as well as to the background pixels. Okay, and check in what sense? So in the following way. So something like this, for example, if you want to, suppose you want to identify the corners in this foreground. Okay, so here are foreground pixels 1, background pixels labeled by 0. Okay, and you want to just identify the corners. Okay, Then here is this example identifies corners. How? So in hit or miss, what will be done is the structuring element will be placed. So the center, by center of course, will be placed at every pixel. Okay, and we will check if there is a matching of foreground elements to foreground elements and background elements to background elements. Okay, so do the foreground elements of the structuring element match up with foreground elements of the image, and background elements of the structuring element match up with the background elements of the image. For pixels where that happens, you keep those pixels in the foreground, and pixels where that matching does not happen, you put it in the background. So what will happen now? For example, with this structuring element, what is going to happen is, see, if the foreground of the image matches here and these are background, then that means that this corner shape is being detected in the image, right? So that means this pixel, this is going to be placed on the center. Remember, imagine that this is placed on an image. Now, if this kind of matching is happening, that means these are foreground and these are background, then that means this pixel is at the corner, right? Corner of the object in the image. And this is how you have detected a corner of the object by this hit or miss transform. Okay. So this is a corner of this, I mean, to detect with a structuring element like this, you will need a corner of this shape, right? So this is your object. Okay, you have placed your structuring element here, and now things have matched up. Let me use another color. So what has happened is you have a match here. So 1, 1, 1, that means these are inside the image, and these 0, 0, 0 are background. Okay, so there's a matching here. So this pixel is going to be kept in the foreground. Okay, and in fact, it is going to be detected as a corner by this transform. Okay, but you also suppose, so this detects only corners of this type, which means lower left. Okay, now you can imagine if you want to detect all kind of corners, you want to detect upper left, upper right, lower right, these 4 kind of corners, then you can then you will need to look at more kind of. So this one, for example, I can write here. So this one is detecting lower left corners, right? This one, the second one is going to detect lower right corners. The third one is going to detect upper right corners, correct? You can just tell that by looking at the structure. And this is the upper left, right? Because this kind of shape is going to be detected, right? The blanks here indicate that you don't really care about what happens in these positions. You could fill these with zeros, okay, and fill this with 1. But it could happen that in your image, you have a corner like this. Okay. If you fill this with 1, then that 1 is not here. So then this corner will not be detected. Okay. So depending on your requirement, you can decide what you want to fill and what you want to leave. Okay. But it should be clear what kind of a mask is going to detect what kind of pattern. Okay. So the hit or miss transform essentially does this. It helps you detect a certain pattern in the image. So based on the pattern that you want to detect, you can design a kernel which will act on both foreground, or which will take into consideration both foreground and background elements. Okay. So these and the way this is done is, first you process the whole image with the first kernel, then you process the whole image with the second, then with the third, then with the fourth, and then the results you can combine together with a logical OR. Okay, so that is how this will work. So then the result of processing this image with these 4 kernels or these 4 structuring elements is these corners. Okay, so this is So you can imagine that the lower left must have detected this one, okay, and this one. These two must have been detected by the lower left. The lower right must have detected all these, okay, this one also, and so on, okay. And then when you put together with the logical OR, then this is what you have. So the net effect is that you have detected all the corners of the object using this morphological transform. Okay. There are also other operators or other convolutions that can, so there is something called the, just like we had this canny edge detection, there is a Harris corner detector. Okay, we did not look at that yet, but we will look at it. There is a corner detector which can, is again a combination of certain filtering, okay, and certain operations, which can also detect corners. Okay. So I'm not saying this is the only one, but this is a pretty decent and simple way. Morphological operations are usually simple to understand. So simpler way of detecting the corners of the so hit or miss will not only detect corners, it will detect any kind of feature that you want detected. Okay, so if you design, so for example, if you design something like this, if you design a kernel, instead of having ones in these positions, if you design it so that it has ones in these positions and zeros everywhere else, okay, what do you think this is going to detect? If I have a kernel of this type and I do the hit or miss transform with this kind of kernel, what do you think this is going to detect? This will detect the lower edge of the image. Okay, anything that is in straight line here. Okay, so something like this will detect the lower edge of the image, and so on. So you can design the structuring element to detect what you want it detected. Yeah, so this is a link to the reference that I've used for these pages for the hit or miss transform, thinning and thickening. For these, I did not use the textbook because it is in the textbook, the description is much more detailed than we require it for this book. Okay, but I just wanted to explain to you what happens. So here, the important thing was this statement. Okay, how the hit or miss transform is working. If the foreground and background pixels in the structuring element exactly match foreground and background pixels in the image, then the pixel underneath the origin of the structuring element is set to foreground color. If it doesn't match, then that pixel is set to background color. Okay, so this statement describes exactly what the hit or miss transform does. Now, the thinning and thickening operations are special cases of this hit or miss transform. Okay, where exactly we will do exactly something like this, but what changes color or how the color is changed is different. So let me describe thinning. Okay, so whatever. So this is the set theoretic definition. So I minus the hit and miss of I and j, where j is the structuring element. Okay, but we don't have to worry too much about this. Let's just see what it does. So for thinning, what happens is you again process in the similar way. You pass your structuring element over all the pixels, and if you hit a pixel where the foreground and background pixels in the structuring element exactly match foreground and background pixels in the image like before, okay, then in this case, what you do is different. Then the image pixel underneath the origin is set to background. Okay, earlier it was being set to foreground if you had a matching. Now it is being set to background. Otherwise, it is left unchanged. Okay, so this is where the difference is. Okay, this is different from before. Then this structuring element is, if there is matching, then this is set to 0. Okay, and otherwise left unchanged. Whereas in here, you were setting it to foreground color, and otherwise you were setting it to background color. Now what? So what is going to happen if The pixel where the matching happens, you're setting it to background color, which means you're removing it from the object. You're removing it from the foreground. So that's going to reduce the number of pixels that are there in the foreground. Okay, so this is some kind of reduction of size of it. Okay, so that's why it's called thinning, because it will reduce the size of it. Okay, but this is different from erosion. Okay, see, in erosion, we didn't need this matching of foreground and background. Correct? In erosion, there was no such matching required. So erosion doesn't really depend on whether the background pixels match up with the background pixels of the structuring element. But here that matters. Okay. So thinning is going to reduce the size in a slightly different way than erosion does. Okay. The other thing is that thinning can be done, is done over and over. Okay. Till you obtain something like this. Okay. Some very sort of a skeleton. Okay, so it can be done in, I mean, depending on your application, you may do thinning only one iteration, but usually thinning is done over and over till some kind of convergence or till some kind of, mm, you know, till you reach a point where if you do thinning anymore, then there is going to be no difference. Okay, that is called convergence. Although in this image, there is something different being shown. So there are two things. One, you do thinning up to you reach convergence, which means any more thinning makes no change. That is usually how thinning is applied. Another point is that thinning can be applied with different kernels. Okay, so you do thinning with respect to B1, then the next time you are not thinning again with respect to the same, but some other kernel. Then different kernels like this. Okay, so just like in hit or miss, we were doing. So this example, we looked at these four kernels. Similarly, in thinning also, you can do thinning with respect to all these different kernels, and you can do them over and over till no more changes observed. Okay. So here in this example, so these are all the structuring elements being used, and this is the set A. So the result of thinning with respect to each structuring element is shown here. Okay. So you can see, I'll just describe the first one. So you can see here that these crosses means we don't care about these two, but we care about 1, 2, 3, 4, 5, 6, 7, these 7. So these 4 foreground pixels and these 3 background pixels we care about. We care about the matching of these. Okay. And so wherever these match, then we will remove those pixels from the image. Okay. So this was the original A. Okay. Now it looks like it was in these. So in these sections, we had this matching. Okay. Why is that? If it is placed at this, if the center or the origin is placed here, okay, or here I should say, then we can see that we have these 4 foreground and the remaining one here background. This is a match. Okay. So then this pixel was set to background color, which means made white, removed from the image, removed from the object, and so on. So there's a matching for all of these. Okay. Up to here, because there is something here. Here, for the next pixel, there is no match, no perfect match. So this pixel was retained. So thinning is hit and miss, or hit or miss, but in this case, you're removing the pixel where the match is observed. And in case of thickening, so here also the important thing is here. If the foreground and background pixels of the structuring element exactly match the foreground and background pixels in the image, then what happens is that pixel is set to foreground. Otherwise, it is left unchanged. So this is where the difference occurs. Otherwise, it is left unchanged. In hit or miss, oh my pencil is discharged. In hit or miss, what was happening is you weren't leaving it unchanged. You were setting it to background color. Okay. But in thickening, what you will do is where there is a match, that element, if it was in the background before, you will set it to foreground. And otherwise, if there is no match, you will not do anything. You will leave it unchanged. Okay. So essentially, what is going to happen is that it could happen that pixels which were in the background earlier change to foreground. So in this way, pixels will get added to the object, not removed anymore. Okay, so pixels get added, not removed, because if there is a no match, then you are not doing anything. Okay, if there is no match, then the pixel is left unchanged, right? So that is why there is no removal of pixels from the object. Only pixels might get added. So thickening will add some pixels to the object, and that is why the object might exactly become larger. Okay, get thickened. So here, this is the object A. Okay, the way to so what they have done here is not directly thickened this, but they have taken the complement of A and they have thinned the complement. Okay, because thickening and thinning are again morphologically duals of each other. So thickening this is same as thinning the background by the complement. Okay. This is the result of thinning the complement, and this is the result of thickening A. Okay. So these are the same, or you can see complements of each other. Okay. Anyway, so I mean, if you forget these two in between, the point is that the thickening of A will look like this. Okay. The last thing that I want to talk about is skeletonization. Okay. So in skeletonization, you find the set of those pixels in the image such that so you suppose I pick up some pixel. Okay, so I look at the largest circle centered at this pixel that will anyway, you just look at the largest circle centered at this that lies inside the object. Okay, now if that circle touches two or more boundary points, then you keep that pixel. Okay, so now if I take a pixel, say here near this boundary, okay, then yeah, let me just draw. If I take this pixel, okay, and I take the largest circle centered at this pixel that is contained inside the object, so then that's going to be something like this, right? Now this does not touch two or more boundary points, right? It touches only one boundary point. Then this pixel I will remove. Okay. On the other hand, if I take this pixel, say here, okay, and if I take the largest circle around this pixel that is contained in the object, then it touches the boundary at these 2 points. In that case, this pixel I will keep. This will be kept. The earlier one will be removed. Okay. Now all the pixels that you keep in this way, okay, in the end will look like something like this. Okay, so these kind of points, for all these points you will have circles that will touch these two boundaries. For these points you will have circles that touch these two boundaries. Okay, for the points here the circles will touch this boundary and this boundary. Okay, and so on. So in the end you will keep these pixels, okay, and remove all other. And this is what is called as the skeleton of that object. Okay, a skeleton for obvious reasons, but the way it is done is this. Okay, so this is done using thinning. Okay, a thinning and opening, I think. No, erosion and opening. Okay, so this is done using erosions and openings, and essentially what it gives you is a very thin 1 pixel thick line, okay, which is called the skeleton of the object. And then the point with skeletonization is you can go back to the original by dilation. Okay, so it has been proved that, yeah, here it is. It has been proved that the original A can be reconstructed from these subsets, which means from the skeleton, by successive dilations. Okay, so if you want to reduce your entire object to just the bare essentials, that is the skeleton, you can do this. And you haven't lost information. If you want to go back, you can use the same number of dilations and go back to the original object. Okay, so skeletonization is a very much used, very often used morphological property. Okay, so sometimes you want to just concentrate on the bare skeleton of the object, okay, without losing information, without losing the object. Okay, so in that case, this is preferred.